In linear algebra, our main topics of study are really linear transformations, both in low dimensions, 2- and 3-dimensional space, but also in higher dimensions, and also in what are called abstract vector spaces. We want to understand that and ultimately relate all those things to differential equations when we are doing a class like differential equations and linear algebra. However, here in lecture 9b, we need to do some other things that are perhaps not absolute requirements for such a course, but I think are good to keep in the course because they are important, for example, in engineering and physics. Dot products of vectors, which we have talked a little bit about to some extent. That will continue here in lecture 9b. Something called the norm of a vector, which is just a generalization of length or magnitude. Angle between vectors and the important concept of orthogonality, which is a generalization of what it means for vectors to be perpendicular. Cross products of vectors, which is special for 3-dimensional vectors. Equations of planes in 3D space, and at the end we'll also relate this stuff back to linear transformations. That is our topics for lecture 9b. Let's move on. To start with, we are going to talk about dot products. So this is something we did talk about before, though just in 2 dimensions. Now we're talking about dot products and norms. Again, lengths or magnitude is another thing that norm means. In n space, n-dimensional space, Rn, which we can think of as either the set of all n-dimensional points, n-tuples of real numbers, or all n-dimensional column vectors that have n rows in one column. You can think of it either way. Here I'm thinking of them as column vectors, given 2 vectors v and w in Rn. So the boldface represents the symbol for the vector, and here we're emphasizing we're thinking of them as being column vectors. The v's and the w's inside are real numbers. These are both elements of n-dimensional space, thinking of that as a set of vectors. Their dot product is the natural generalization of the dot product for 2-dimensional vectors. Do you recall what that was? If we had 2 two-dimensional vectors, back, I forgot what lecture it was, maybe lecture 3 or 4 or 5 or something, we talked about how to find the dot product of those 2 things. It was A times C plus B times D. It is a real number. It's in R. The dot product of 2 vectors is not another vector. It's a real number. That's very important to remember. This generalizes that. It's still a sum of products of the corresponding components. That's what you see here. V dot W. And make sure you put the dot in there. I'm making it extra big to emphasize it. You don't have to make it extra big. Make sure you put that in there. Make sure you make it clear that those are vectors either by typing with boldface or by hand with vector half arrows like this. And then realize that these other v's and w's are real numbers. We are adding up the products of the corresponding components. v1 times w1 plus v2 times w2 plus v3 times w3, etc., up through vn times wn. In summation notation, which you should be comfortable with, you can also write this as the sum, I goes from 1 to n, of vi times wi, like that. And don't make those v's and w's boldface. Don't put little half arrows above them. We think of those as numbers. Leave them as regular looking letters. Properties of dot products. At the end of lecture 8b, we talked about algebraic properties of vectors like the commutative property, for example, and I said those properties should not be ignored. They are a big part of the course. To make sure you remember those as well as their names. These properties that I'm about to show you are also very important and worth remembering. There is a commutative property for dot products. V dot W equals W dot V. How would you prove that? Well, it's based on the commutative property for real numbers. If I could, just to save time thinking of it in terms of summation notation, I could also write this as the sum I goes from 1 to n of Wi times Vi. I can switch around those products. And according to this definition, that would be the same as W dot V. Okay? Say the word dot, make sure you put an actual dot in there. There's a distributive property. U dot, in parentheses, V plus W, which means find V plus W first, then dot it with U. is the same as adding up these two real numbers, u dot v and u dot w. Everything here ultimately is a real number. V plus w is a vector, but then when I dot it with u, I get a real number. These two things, u dot v and u dot w, are both real numbers, but then I'm adding those two real numbers. This equality does hold. It's so important to keep track of what's a vector and what's a number in your mind to really understand what's going on. Much more important than you might realize. There's an associative, I put associative slash commutative property. It's an associative property because I'm changing where I put the parentheses. It's a commutative property because I'm kind of changing where I put the lambda. V and w are vectors, lambda is a scalar, a number. This would mean do lambda times v first, then dot it with w. This would mean do lambda times w first, then dot it with v. This would mean do v dot w first, then multiply times lambda. That's a scalar multiple of a vector, dotted with a vector to get a number. This is the same kind of thing. This is a dot product of two vectors to get a number times a number. This is not a scalar times a vector there, ultimately. Non-negativity. When you dot a vector with itself, you can't get a negative number. That's what this is, right there. V dot v is greater than or equal to 0, and in fact, the only way v dot v actually equals 0 is if v is the 0 vector. Notice what's boldface and what's not. This is not boldface, that's a number. The number is 0. If I'm talking about the 0 vector, I can't put a greater than or equal sign in there. These two things are numbers. This number is greater than or equal to this number. You can't, v dot v is not going to be negative. This is the number 0. This is the 0 vector. Keeping track of those distinctions helps you understand things better. Why is this true? It's not too hard to prove. V dot v, by this definition, is really v1 times itself, so it's v1 squared, plus v2 times itself, so it's v2 squared, etc. The last term is going to be vn squared. These are real numbers, so there's no way any of these squares are going to be negative. This is going to be greater than or equal to 0. And yeah, the only way this could possibly equal 0 is if all these v's are 0. And therefore, v vector is the 0 vector. What's a norm? Also known as magnitude or length of a vector. We talked about norms back with two-dimensional vectors as well. If v is the column vector AB, I wrote that the magnitude of v, the length of v, the norm of v, by the Pythagorean theorem really, if you draw it, is the square root of the sum of the squares of its components, which I also noted is the same thing as the square root of v dotted with itself. Same thing here, just generalize it. Does it make sense in n dimensions when n is a million? That's not so easy to answer. It does make sense in 2 dimensions. It also makes geometric sense in 3 dimensions if you draw pictures and think about the Pythagorean theorem. And it does turn out to be a good idea to generalize it to n dimensions where n is an arbitrary positive integer as well. So this is what you get. The norm of v, the magnitude of v, the length of v, you can use all those names. The word norm is the one that generalizes to more abstract settings. Is the square root of the sum of the squares of its components, which is the same as the square root of the vector dotted with itself. This has properties that you should know as well. Properties of norms. Non-negativity, just like there was a non-negativity property for dot products, is that the norm of any vector can't be negative. It must be greater than or equal to 0, and the only way the norm of a vector equals the number 0 is if the vector is the 0 vector. If and only if means it goes both ways. If this is true, then this must be true, and vice versa. If this is true, then this must be true. There's what you might call a factoring out of absolute values of scalars. Maybe not the best name, but here's what the property is. The norm of the scalar lambda times the vector v is the same as the absolute value of the scalar times the norm of v. Not going to prove this, but you can just check it. Think about proving it on your own, or think about examples. And then there's something called the triangle inequality. It says the norm of v plus w is less than or equal to the sum of the norms of v and w individually. This is not super easy to prove, but it does make visual sense. If I think about the head to tail definition of vector addition, if this is v and then I add on w by putting its tail at the tip of v, then v plus w is this vector here. And essentially what the triangle inequality says is that the length of this side of this triangle is less than or equal to the sum of the other two lengths. Another way of saying that is the shortest distance between 2 points is along the straight line between them. So in that sense, it makes, it's pretty obvious, you might say, it makes a lot of sense. And maybe you can't quite see that. That happened in the last lecture. Here's I drew v, w, and then v plus w. These are supposed to be straight. I drew that one kind of curved. Okay? The triangle inequality is super important in higher level math. It's not going to be super important for us, but it might come up once in a while. Another inequality is called the Cauchy-Schwartz Inequality. Please say Cauchy, don't say Cauchy. Cauchy. And angles in M space can be thought of based on the Cauchy-Schwartz Inequality. Let V and W be an Rn. Then you can conclude that the absolute value of v dot w is less than or equal to the products of the norms in v and w, or v and w individually. This is not super easy to prove either, but it is true, and it is pretty important, once again, in higher level math. Not so much for us, except maybe right now. Turns out, in terms of components, this is equivalent to this statement, because there, and I essentially take this inequality and square both sides. Here's the v dot w is the summation there, and I'm squaring that. The square root of this quantity there would be the norm of v. The square root of this quantity here would be the norm of w, so these equations are equivalent to each other. Here's a corollary. Suppose v and w are non-zero, so that their magnitudes, their norms are non-zero. I can take this inequality and divide both sides by this positive quantity and get this inequality. That the length, or the absolute value of v dot w is less than or equal, or divided by the norm of v times the norm of w is less than or equal to 1. That turns out to be a pretty important fact for defining an angle between vectors. Let v and w be an Rn and non-zero. The quantity theta equals arc cosine of this thing. Oh, you know what? Here's a typo here. And let me change the, no, I can't change it on this thing. The absolute value sign should go away. And I can also say this thing right here is equivalent to saying this is true. That fraction is between -1 and 1. Theta is defined to be the arc cosine or inverse cosine. Those are the same function. I'm writing it both ways to emphasize those are the same thing. You should know that from calculus. Of v dot w over the length of v times the length of w. This is a real number between 0 and pi based on the definition of the inverse cosine function, and is defined to be an angle between v and w. Is it the only angle? Well, no, because you could add multiples of 2 pi to it, integer multiples of 2 pi. You could also subtract it from 2 pi. 2 pi minus theta would be sort of like another angle between them. Like, that makes sense if you think about a picture. V is here and w is here. There's theta. That would be between 0 and 2 pi, 0 and pi if you thought of it as a positive angle, but you could also think about a negative angle going that way. Or a positive angle going the other way, which would be 2 pi minus theta. This definition is possible because of the corollary, because this is less than or equal to 1, which is equivalent to this. The inverse cosine function, if you want real number outputs at least, has a domain between -1 and 1. inclusive, the closed interval from -1 to 1. But does this definition make sense? Is this a good idea? It is consistent with something else we talked about with two-dimensional dot products. The geometric definition of dot products is that v dot w is the length of v times the length of w times the cosine of the angle between them, when we assumed we could think about that angle in a picture like in a 2- or 3-dimensional situation. And I mentioned to verify this fact, you would use the law of cosines, though then you might wonder why is the law of cosines true. This equation is consistent with that, because you can, if you solve this equation for theta by dividing both sides by this and then taking the inverse cosine, you will get this, which again is the same as this, just a different name. So it's consistent with this, and so in that sense it makes sense. Is it a good idea? Do we want to define angles between vectors in million-dimensional space? That's less obvious, but I claim it is still a good idea. Especially when we happen to think about vectors that happen to be perpendicular, as I will mention here in a moment. That's about what I'm about to mention right now here. Actually, a very important note. Assuming once again the v and w are non-zero, we see that the angle is 0 if and only if what? What angle has a cosine of 0? What angle between 0 and pi radians has a cosine of 0? Pi over 2 does. 90 degrees. Theta is 0 if and only if, and that's a typo. That's a typo. I might have been confused as I was talking about it. Yet another typo here. Got to make sure I make changes. This is not supposed to be 0. It's pi over 2. Theta is pi over 2, 90 degrees if and only if v dot w is 0. V and w are perpendicular when they are non-zero, if and only if v dot w is 0. Dot products can be used to detect perpendicular vectors. And this leads to a new definition. Two vectors v and w, non-zero or including 0, are said to be orthogonal if their dot product is 0. So orthogonal is essentially synonymous with perpendicular, though we are allowing v or w or both to be the 0 vector here. But the better reason to use a different word is this is going to generalize not only to higher dimensions, but to more abstract situations. And these abstract situations do have applications that I'm hoping we can see at the end of the course when we hopefully have time for partial differential equations. The application of orthogonality in more abstract settings applies to helping you figure out, for example, solutions of partial differential equations related to something called Fourier series. Real important in science and engineering, actually. Equations of planes in 3-space. This page is just a specialized page that is going to lead us to the next page on cross products here. But it's also helpful for thinking about linear transformations as well, and their kernels or images, as we've talked about recently. A linear equation of the form ax plus by plus cz equals 0. A, b, and c are constants, x, y, and z are variables. Always defines a plane through the origin in R3. Well, at least if one of those coefficients, a, b, or c, is non-zero. And if I'm writing the equation like that to begin with, I'm kind of really assuming at least one of those is non-zero. If they're all 0, then I just get the equation 0 equals 0, which is not something that we're interested in thinking about, though it's true. In fact, since this vector ABC dotted with this vector xyz equals ax plus by plus cz, the left side of this equation, we can say that, listen carefully here, the fixed non-zero vector, call it n, ABC, there's a good reason I'm calling it n. It's because this, it's called a normal vector, is orthogonal, perpendicular to an arbitrary vector x equals xyz, which is if you assume it's parallel to the plane, or in the plane, when you put its tail at the origin. Get this? This equation is saying, if I know what A, B, and C are, that this vector is a fixed vector that's going to be perpendicular to the plane containing an arbitrary variable vector that I'm pretending lies in the plane. Maybe that's still confusing. It lies in the plane if the tail of the vector is at the origin. And it also turns out that any equation of the form ax plus by plus cz equals d defines a plane as well. And it's parallel to this one going through the origin if d is non-zero. If d is non-zero, it's a different plane, but it's still parallel to the original one. If d is zero, then it's the same as the original one. And if d is non-zero, it's not going to go through the origin. So, given a normal vector n for a plane and a point in the plane, it is easy to find an equation of the plane and vice versa. So, for example, if I pretend I know that n equals 7, -3, -5 is a normal vector for a plane, and I pretend that I know the point corresponding to position vector 1, 2, 3 is in the plane. That corresponds to the point 1, 2, 3, pretending that's in the plane. I know I can take these numbers, 7, -3, -5, as my A, B, and C, to say the left-hand side of the equation for this plane looks like this. And then I can figure out the D on the right-hand side. Oops, hopefully this is not too far. The D on the right-hand side by plugging the point into the left-hand side to see what D happens to equal. 7 times 1 minus 3 times 2 minus 5 times 3 is 7 minus 6 minus 15. -14 happens to be the D. So the equation of the plane with this normal vector containing this point, 1, 2, 3, corresponding to this position vector, 1, 2, 3, has equation 7x minus 3y minus 5z equals 14. And vice versa. If you know the equation of the plane is this, then you're going to know this is a normal vector, 7, -3, -5, and you can figure out points in the plane if you want as well. On the other hand, for a given plane, say specified by 3 points that are not on the same line, noncollinear, how do we find a normal vector n, and then how do we find the equation of the plane as well? If you're taking notes, you can add in, how do I find the equation of the plane? All right, hang with me here. You need the idea of a cross product. Sorry about the extra noise here. I'm near some other people's offices. You need the idea of a cross product. Given two vectors, v and w, in R3, these must be three-dimensional vectors here to do a cross product. Their cross product, unlike a dot product, is not a number. It is another three-dimensional vector. It's defined by a quite crazy-looking equation. This equation here. V cross w, or this vector cross this vector, and you should put the cross in there, the time, so to speak, but say the word cross, equals this three-dimensional vector. What in the world? The first component of this vector is a cross product, so to speak, of the other components. V2 times W3, but then with a minus sign, V3 times W2. So it's like I'm doing a cross within the vectors, but also with a minus sign. It's that way for the first component. For the third component, it's the same way. Sort of ignore the third component and focus on the cross product of the other two components. V1 times W2 minus V2 times W1, that's what you see there. And for the middle component, the second one, you focus on crossing between the first and third, except you need an extra minus sign in front. So we do V1 times W3 minus V3 times W1, but then put another minus sign in front, which means you can also distribute the minus sign through the parentheses, of course, as well. What in the world? Where did this come from? Probably the first person to discover this did a lot of experimentation. Why would they do such experimentation to come up with such a crazy formula? Because of the properties of the cross product. It has very nice properties that are useful. First, there's what I call a second power nilpotency. When you cross a vector with itself, you get the zero vector. Cross a three-dimensional vector with itself, you get a three-dimensional zero vector. It's almost like we're squaring V, but don't call it a square. That's why I put the word power in quotes. Anticommutativity. What? Anti? Yeah. V cross W is the opposite of W cross V. You're switching around the roles of the V's and the W's, and with the minus signs in there, it should make sense. The answer can't be the same, and in fact, it's going to be the opposite. Weird. There's a distributive property. Not an anti-distributive property, a regular distributive property. Cross product distributes over vector addition. V plus W, then cross with U, putting the U in the front, is the same as the sum of these two three-dimensional vectors, U cross V and U cross W. Perhaps most important is the magnitude property. The length of the vector V cross W, its magnitude or norm, is the norm of V times the norm of W times the absolute value of the sine of the angle between them. I guess maybe cross products can be used to define angles as well, but you need to be a little bit more careful if it is. You do need the absolute value signs around the sine, whereas with dot product you don't need an absolute value sign around the cosine. Dot products can be negative, but cross products are vectors. They can't be negative. It doesn't make sense. And their lengths can't be negative either, so you do need the absolute value sign there. On the other hand, if theta is, you say theta must be between 0 and pi radians, the sine of theta would automatically be non-negative in that case. So this is only relevant if you allow for angles that are not between 0 and pi. It's related to orthogonality as well. V cross W is orthogonal to both V and W. That's a fact. If you dot V cross W with either V or W, take V cross W and dot it with V, for example, you get the number 0. And same thing if you dot it with the vector W, you get the number 0. So V cross, oops, there's a typo there. There's a cross blank there. V cross W is orthogonal to both V and W, and W cross V is orthogonal to both V and W. In fact, W cross V, because of this, points in the exact opposite direction as V cross W. And this is useful because of property 5. 4 and 5 are really the most important ones. This is useful because if we got a plane, and we know 3 non-collinear points in the plane, then we can figure out a couple vectors that are parallel to the plane. Say this vector and this vector. And by finding their cross product, we can find a new vector. This is V, this is W. Say this is V cross W here. We can find a new vector that's perpendicular to the plane, and that will then be a normal vector for the plane. By the way, based on this drawing, V cross W really would point in this direction. There's something called the right-hand rule that I'm not describing. I would say it goes in that direction. I'll wait maybe for the next lecture to do that. So coming back to this, if we've got 3 distinct non-collinear points not on the same line, how do you find the equation of the plane? First, let V be the vector whose components are the differences x2 minus x1, y2 minus y1, z2 minus z1, and let W be the vector whose components are x3 minus x1, y3 minus y1, and z3 minus z1. Let n be V cross W or W cross V, it doesn't matter. And the equation of the plane is then n dot this vector. I picked x1, y1, and z1. I could have used x2, y2, and z2, or x3, y3, and z3. When you simplify, you'll get the same answer either way. It can be simplified to this kind of form here. ax plus by plus cz equals d. Not going to take the time to do an example to illustrate this. My students will have exercises where you do this. It's not hard. Just go ahead and do that. And you will get an equation for the plane. Just follow this procedure, then I hope it makes sense based on knowing property 5, that V cross W is orthogonal to both V and W. You'd have to verify these facts, and that would be a good exercise too. Maybe I'll assign it for my students. We've got 2 more slides for this lecture. I do want to, at the end of this lecture, relate these things back to linear transformations. Again, that's our main thing of interest. So let's just consider a particular kind of linear transformation here. From R3 to R1. 3-dimensional space to 1-dimensional space. You don't see a 1 there, but I could put a 1 there. Defined by t of x equals a times x. Okay? I'm going to think about this in the abstract first, then we will look at a particular example to finish off the lecture. So here it is in the abstract. T of x, x is a 3-dimensional vector, a 3x1 column vector, components x, y, and z, is supposed to be a number, and this is supposed to be a linear transformation, so the formula better be of this form, ax plus by plus cz. Now we're seeing the connection between what we just talked about. That can be thought of as a 1-dimensional vector, or matrix if you like, a 1x1 matrix. It can also be thought of as the product of this 1x3 matrix with this 3x1 matrix column vector to get a 1x1 matrix, which is a number. But I could write it using a times x notation if I wanted to. A is this 1x3 matrix. Should we call that a row vector? We could, actually. X is this 3x1 matrix, which is a column vector, a 3-dimensional vector. Ax equals this. Let's think about onto and one-to-one again, like we did in lecture 8b. Such a function like this is going to be onto if and only if this matrix, capital A, is not the 0 matrix, not the 1x3 0 matrix. And that's going to be true as long as one of those numbers, A, B, and C, is non-zero. And when it is onto, using image notation, we can say the image of T, the linear transformation, is all of R. This is the domain, R3. This is the codomain, R. That is the same as what we call the column space of A. I did mention that in lecture 9b. T as a function and A as a matrix are related to each other. The set of all outputs of T is called the image of T. The set of all products of A times X like this is called the column space of A. It's really the set of all linear combinations of the columns of A. Just introducing this idea. We'll come back to it later, plenty of times. It's all of R if it's onto, and it's not all of R if it's not onto. And it's not going to be onto if A is the 0 matrix. I put 0 with a matrix there. That would really represent 0, 0, 0 there as a row matrix there. If that's true, then in fact the image and kernel, or excuse me, column space are just the number 0. Just one point. Everything is getting mapped to the number 0 there. Such a function will never be onto, or excuse me, never be one-to-one, never be injective. If A happens to be the 0 matrix, in fact, the kernel of T is all of R3. Everything gets mapped to 0. Kernel of T, also called the null space of A. Image of a linear transformation is the same as the column space of its matrix. The kernel of a linear transformation is also called, and is the same thing as the null space of its matrix. Everything is getting mapped to 0 in that case, so the kernel of T is all of the domain, R3. And if A is not the 1x3 0 matrix, then the kernel, the null space, will not be all of R3, not equal to R3. What will it be? It'll be, think about it, a plane to the origin, defined by the equation ax plus by plus cz equals 0, just like we talked about, with normal vector ABC, written as a column vector, I guess. Let's consider a particular example. This is our last slide. Describe the kernel of T going from R3 to R, defined by this formula. So the matrix capital A is this 1x3 matrix 3, 2, -4. Current T is the set of all points in R3 that satisfy the equation 3x plus 2y minus 4z equals 0. That's going to be a plane through the origin. That's perpendicular to this vector 3, 2, negative 4, if you think of it as a column vector, as we always have. That'll be a normal vector. Also notice that this is our final observation, though I maybe want to try to make a graph of this plane. This is our final symbolic observation. T of x equals a times x, which is this, is the same thing as this, and that's a dot product right there. That's no accident. It's purposeful to relate matrix times a vector to dot products. We define a matrix times a vector as a linear combination of the columns of the matrix with the entries of the vectors as their weights. But this can also be related to dot products, and you may have learned matrix multiplication thinking in terms of dot products before. Let's end by trying to draw this plane here to the best of our ability. Mathematica, by default, makes a positive x-axis go to the right. You can change that setting to make it kind of come out of the board or paper at you, but let me draw it like Mathematica does here. Positive y-axis going this way, positive z-axis going this way. Of course, then there'd be negative directions for these axes, which I'll make with dashed lines. This is a rectangular coordinate system for a three-dimensional space. Plane is going to go through the origin. It's going to have normal vector 3, 2, negative 4. X component of 3, y component of 2, and z component of negative 4. Try to imagine like a box bounded by these lines here. Some people can see this kind of thing well, and some people have a hard time with it. The vector is going to go from the origin down to the opposite end of that box, which is behind the board, so to speak, in this picture. That'll be a normal vector for the plane, perpendicular to the plane, which means it's going to be hard to draw this plane. That's going to be perpendicular to it. Maybe something about like this. And that's going through the origin. This plane's got to contain the origin. It can be very difficult to try to draw. Some people are much better at it than others. And this is supposed to be a plane, not a box. I shouldn't have all these different lines on the same size of the plane. And it goes on forever. Okay? So these ideas are pretty important. They're sort of specialized for this lecture, but we will use them from time to time in the future. Thanks for watching.